Assalamualaikum and hello to everyone. My name is AMIRUL HISSAN bin RAJJAB and I'm from group 23. Okay, today we are going to talk about surface tension and capillarity. So, before that we need to know that due to molecule extraction, liquid possess certain properties such as cohesion and adhesion. So we need to know what adhesion and cohesion. Cohesion is the same molecule that stick together. Like, for example, cohesion between water molecule and hydrogen bonding, and the other one is adhesion. Adhesion means the different molecule that stick together. For example, water molecule between adhesion between water molecule and wall of the container. So that is the picture that I draw. So this is adhesion for the green arrow that I made, okay, and the other one is cohesion for the pink arrow. Okay, so we move to the surface tension. What is surface tension? Surface tension is a measure of the force necessary to stretch or break the surface of liquid. An effect within the surface layer of a liquid that causes the layer to behave as an elastic sheet, or the arrangement of water molecules at the interface between water and air, hydrogen bonded to one another and to the water below. This effect allow insects like water strider water strider can walk on the water surface and allow small things like needle float or sink on water surface. Okay. This is surface tension that I draw. Okay. So for capillarity, when what is capillarity? When a liquid possesses relatively greater affinity for solid molecule, or the liquid which have greater adhesion than cohesion, then it will wet a solid surface in contact and tend to rise at the point of contact. Such liquids are called wetting liquid. Like is wetting liquid. Okay, in this case, the angle of contact between liquid and the solid surface is less than 90 degree. Okay, less than 90 degree. An example of such liquid is water. For example, if a glass tube of small diameter is partially immersed in water, the water will wet the surface of the tube and it will rise in the tube to some height above the normal water surface. In this case, the water surface is concave out. So for wetting liquid, it is concave out. On the other hand, if a liquid has less than attraction for a solid molecule, Or in other words, the cohesion predominates over adhesion, then the liquid will not wet the solid surface and the liquid surface will be depressed at the point of contact. In this case, the angle of contact between liquid and solid surface is more than 90 degrees. For example, such liquid is mercury. So that's the picture, the diagram that I draw. So for non-wetting liquid is more than 90 degree. Yes. Okay. For example, if a glass tube of small diameter is partially immersed in mercury, the mercury will not wet the surface of the tube in contact, and the level of mercury inside the tube will be depressed, or it will be lower than the normal mercury level. It changes the level of mercury. This means in this case, the mercury surface is concave downward. So from that, we know that for wetting liquid is concave outward, and the other one for non-wetting liquid is concave downward. Okay, so we have two example for these topics, which is this rise or fall of a liquid. For rise of liquid, like that, the diagram. So for the rise, capillary rise is due to adhesion, and capillary fall is due to cohesion. Therefore, capillarity is due to both adhesion and cohesion. Means that the both of rise and the fall of liquid is involved of cohesion and adhesion process. Okay, we move to Stokes law. Okay, Stokes law. We have seen how viscosity acts as a frictional brake on the rate at which water flow through a pipe. Let us now examine its frictional effect on an object falling through a viscous medium. To make it simple, we take a sphere like ball bearing, and if we use a very viscous liquid such as glycerin and a small sphere that I mentioned before, for example a ball bearing of radius a millimeter or so, it turns out experimentally that the liquid flows smoothly around the ball as it falls with a flow pattern. So like this. This is error. Okay. If we knew mathematically precisely how the velocity in this flow pattern were very near the ball, we could find the total viscous force on the ball by finding the velocity gradient near each little area of the ball surface and doing an integral. But actually, this is quite difficult. Known as Stokes law, it was done in the 1840 by Sir George Gabriel Stokes. He found what has become known as Stokes law. So the drag force on a sphere of radius A, which is A, and moving through a fluid of viscosity, and the other one is at speed with u is given by F equal to 6 pi A and U. This drag force is directly proportional to the radius. That's not obvious. One might have thought it would be proportional to the cross-section area, which would go as the square of the radius. The drag force is also directly proportional to the speed, not, for example, to V squared, U squared. Okay, that's all. Thank you.